This is a simple half-wave dipole. Viewed from above, it looks like this. And we can represent its radiation pattern as a series of expanding circles. It is often desirable to concentrate this radiated energy into specific areas. In other words, we wish to make the antenna more directive. To see how this is achieved, let us return to the omnidirectional pattern. Here, red represents the positive peaks and blue the negative peaks. The distance between two peaks of opposite polarity is 1/2 a wavelength. We will introduce a second dipole spaced 1/2 a wavelength from the first. If we feed both dipoles 180 degrees out of phase, we obtain this radiation pattern. In the plane broadside to the antennas, the waves are 180 degrees out of phase with each other. The waves propagating in this direction thus cancel each other out. Useful propagation has thus been achieved in two directions, by feeding the dipoles 180 degrees out of phase. If we feed the dipoles in phase, we obtain this radiation pattern. This time, waves in the plane of the antennas are out of phase. The waves propagating in this direction will thus cancel each other out. By feeding the dipoles in phase, we again achieve useful propagation in two directions. By adding extra dipoles 1/2 a wavelength apart, we can concentrate the radiated energy still further. Let's now review how bidirectivity is achieved. A single dipole with its omnidirectional radiation pattern produces a donut-shaped polar diagram. By adding a second dipole 1/2 a wavelength from the first, we have altered this polar diagram to produce two lobes. By increasing the number of dipoles, we have sharpened these lobes. To aid this presentation, the antenna size in relation to the polar diagram is greatly exaggerated. These bidirectional qualities are thus produced by spacing dipoles 1/2 a wavelength from each other and feeding them in phase or out of phase. Three practical examples of this type of array are the broadside, the collinear array, and the end-fire array. All these antennas concentrate the radiated energy in two directions. In some cases, however, it is desirable to concentrate the radiated energy in one direction. To see how unidirectivity can be achieved, let us return to the simple dipole. A quarter of a wavelength from it, we add an undriven element which acts as a reflector. Again, we can view the elements from above. A wave leaving the antenna reaches the reflector a quarter of a wavelength later. Due to inductance, a wave of opposite polarity is produced. When it reaches the antenna a quarter of a wavelength later, it is in phase with the wave then being created. The resulting radiation pattern looks like this. Notice that in this direction, the waves cancel each other out, while in this direction, they reinforce each other. Unidirectional radiation is thus achieved by adding a reflector a quarter of a wavelength from the dipole. And the polar diagram shows how the radiated energy is now concentrated into one lobe. Similar lobes can be produced by adding suitable reflectors to our three typical antennas. Here is the broadside, the collinear, and the end fire. The upper VHF region sets the practical limit to this type of array. It is more convenient to control the radiated energy and narrow the beam width in the microwave region. Because the microwave region is close to that of visible light, we can now use optical principles to solve our radiation problem. Let's briefly review a simple optical principle. Here's a plane surface. Light, striking it at this angle, will be reflected at an equal angle. If we arrange a number of such reflecting elements so that the reflected rays emerge parallel to each other, our reflector becomes a parabola. All path lengths from the focal point will be equal. Energy will thus radiate in a plane of uniform polarity and intensity. The practical parabolic reflector is three-dimensional, and this type of antenna concentrates the radiated energy into a single lobe. It thus provides maximum directivity for transmission with good capture area for reception. Other antennas can be derived from the basic parabola, such as the parabolic cylinder, the orange peel paraboloid, and the cosecant squared antenna. All these antennas are made directive by the application of simple principles. From the simple dipole with its omnidirectional radiation pattern, which produces a donut-shaped polar diagram. We can arrange the feeding and relationship of additional elements to change the radiation pattern. And produce a bidirectional polar diagram. We can further concentrate energy by the use of reflectors. And a unidirectional polar diagram is produced. The application of these simple principles facilitates the design of antennas which concentrate energy and increase receptivity in the desired direction.